Welcome to the last session in this class, and in this last video, what I want to share with you, we want to discuss the lab in terms of simulation and analysis. We are going to talk about the topics of Thevenin's theorem, Norton's theorem, and then I'm going to give you an example of the circuit analysis techniques where I'm going to use all of the techniques on a single problem. So we have one problem to solve, and we're going to use different techniques to solve that problem. Following this, I'm going to give you some information about the project that you can work on. And again, it's a programming project. You need the Arduino that you have, and so there are a few steps to follow so that you can complete.
We're going to review this lab very briefly. Again, this lab is a review of multi-source techniques that we discuss in the class. We look at two different circuits and we go through and we look at the analysis techniques. Let's go ahead. Let's make this a little bigger. So again, what are the objectives of this last lab? Again, this is to help you prepare for your final exam. We want you to become familiar with the techniques for solving multi-source circuits, and these are the loop current method, branch current method, nodal analysis method, and also superposition method to solve the unknowns for a circuit with more than one power source. Also to measure the unknowns in a multi-source circuit using simulation. So the equipment for this lab is simulation. So we are saying that there are some circuits where we cannot just use the principles of series and parallel rules to obtain the currents flowing the circuit, because we have currents from this source and currents from this source, and they're going to interact with each other so that we cannot directly calculate it. That's why we need to use these different techniques. So in this lab, what you will see is that we are not really interested in the answer. We are interested in you using the technique. So the answers, we find the answers using simulation, and we use these answers to verify our solutions using the techniques. So again, this circuit has two sources. Look at the simulation results. It tells us that total current flowing here is 5.25 amperes. The total current, and again 10 is negative, tells us it's going in the opposite direction. The total current flowing through here is 2.66 amperes. The total current flowing through here is going to be 7.91 amperes. And again, when it's negative, it tells us that the current direction is switched. And again, we also got the voltage at this node, which is 24 volts. Makes sense because the battery is connected here. So we have two different circuits, and again, in this lab, we give you the answers we use two techniques for the first circuit and two techniques for the second circuit, and we ask you to do the same. Just flip it around, right? You'll do the other two techniques for the first circuit and the other two techniques for the second circuit. Again, here, this is the second circuit here. So again, here, again, the steps for each technique is presented to you. In the procedure, exactly what I said, it tells you to use the particular technique to solve the circuit in figure 2. And then it tells you use the other two techniques to solve the other circuit that was not solved and put your results in the lab worksheet. So let's look at the techniques that were solved. So you can see here, this is procedure 1, where we are using these two techniques to solve the circuit in figure 2. So again, here you see this is the branch current method being followed, and there's a video explaining. The video actually shows how this analysis was completed, so I would encourage you to watch the video. Likewise, we have a video showing how this mesh current method was also completed. For the next circuit, we have the other two techniques. So you can see that for this circuit here, we're using superposition, where we use one source at a time. And for the last circuit, we use the nodal analysis to obtain the currents as well. So you can see the results here for figure 2. Notice that the results from simulation are the same as the results from the superposition and the nodal analysis. How do you find the voltage across the components? You simply multiply the final current by the resistance, and you can find the voltage drop across the components. So this is what you have to do. So in this lab, the lab worksheet is attached for you to also complete it. Follow the instructions. Like I said, so for example, for the first circuit, I use the branch current method for this one, and I use the loop current method for this one as well. So the procedure asks you to solve this same circuit using the superposition theorem and the nodal analysis method. Now for the second circuit, I use superposition and nodal analysis, and it asks you to use branch current and loop current to solve the unknowns for this circuit, so that at the end you use all the methods.
Step is to draw the circuit. First step is to draw the circuit. And the first problem asks us to use the branch current method and the loop current method. So we're going to draw the circuit. So I'm just going to write here. This is our circuit that we're working with. So our I1 is going to be the current on this side, I2, this is going to be I3. Alright, so this is 24 volts, this is 3 volts, this is 6 ohms, this is 9 ohms, and this is 4 ohms. Okay, so let's write the key here. Okay, so this is the first step to draw the circuit. The second step is for us to go ahead and do the branch current method. Now, anytime we do the branch current method, the first thing we need to do is to assign the directions. Then we're gonna put the polarities. So I'll just put polarities. And I already gave this to you in the lab handout. The second step, we're going to write the KCL. Kirchhoff's voltage law equations for each branch, and also we write the Kirchhoff's current law. And then of course we're going to write the equations in standard form. Following this, we need to solve these simultaneous equations. So there are different ways to solve them. All right, this is the next thing we need to do. All right, so again, here, I'm going to, since we have the circuit here already, I'm just going to put some branch currents on here and assume that the currents, so let's say the current is going in this direction, let's say it's going in this direction, and let's say we have current going in this direction. So I can write an equation based on this. So if the current is going there, where the current enters, we need to put a plus on this side, and then we're going to write the equation. So the equations are going to be, we can start right here. Again, what we are writing for the KVL, we are just saying that the voltage drops is going to equal to the source. So the voltage drops here will be equal to the source. And so to find the voltage drop, we take the current going through the resistor times the resistance of the resistor. So I can start right here. I can say that 4I1 plus 9I2 is equal to 3. That's essentially what we are saying. Another way you can say that 4I9 plus 9I3 minus 3 is going to be equal to 0. On this side here, we're going to have here 6I2 plus 9I2. Sorry, that's 6I3. So this is I3 here. So 6I3 plus 9I2 is equal to 24. All right. So the next step is to write it in, and then the Kirchhoff's current law, we can say that I1 plus I3 is going to equal to I2. I1 plus I3 is equal to I2. And we can rewrite, if we put I2 on this side, we're going to have I1 minus I2 plus I3 is equal to 0. So that's the first step. We need to also write it in standard form. So to write it in standard form, we're going to put all the variables here. So we're going to have 4I1 plus 9I2 plus 0 is equal to 3. Likewise here, we're going to have 0I1 plus 9I2 plus 6I3 is equal to 24, and we can write this equation here as well. It's going to say 1I1 minus I2 plus 1I3 is equal to 0. So this is our equation here. We can now solve it using the simultaneous equation. So to write it, essentially what we are doing, we are obtaining the solution for this matrix. So I can write the matrix here. We have 4. So all the constants here, I gotta go in the matrix. So it's the constants, and this is the unknowns. I1, I2, I3. And we have the solution, which is 3, 24, and 0. So this is the matrix. We are multiplying these 3 by 3 by the 1 by 3, and this is what we're supposed to get. And so to find the unknowns, we're going to use the determinant method. So again, we have now the simultaneous equations here. So we have done this, we have done this, we have done this. We have done the standard form. This is the standard form right here. Now we're going to solve the equations using the determinant method. Again, there are different ways you can solve it. So in this case here, I'm going to start by getting the determinant. I'll call it the primary determinant of a 3 by 3 matrix. So for that, you need to repeat the first 2 columns. And the way we get the determinant is we need to multiply these and subtract them add them together and subtract them from this. So doing this, we get this 4 by 9 by 1, which is 4 by 9, which is 36. And we're going to add it to 9 by 6. By 6 by 1. Yep, and that's 0 here. So then we're going to subtract. What are we subtracting? We have here 1 by 6 by 4. So again, we're going to subtract this negative 6 by 4. And so that gives us a positive 24. So plus 24. And of course, this is 0 as well. So what does this come to? This comes to 36. This comes to 54. And so when we add this together, we get 114. So this is our primary determinant. And so to find I1, we need to replace the first column with the answers, and then we will divide it by the primary determinant. So I1 is going to be equal to, so I'm gonna replace the first column with the answers. 3, 24, 0, 9, 9, minus 1, 0, 6, 1. And again, I repeat the first 2 columns, 3, 24, 0, 9, 9, minus 1. And of course, same thing, we're going to multiply these and subtract them from this. So that gives us, and of course, we divide it by the primary determinant, which is 114. So that gives us here 3 by 9 by 1, 27. So I'll just write the number, 27 plus all this is 0, 9 by 6 by 0. So we're going to subtract. What are we subtracting? We have 6 by 3, which is 18. So minus and a minus will be a plus. So plus 18. And then we have minus. We need to subtract this from 24 by 9, which gives us 216. And so when this will come to 171. So 171 over 114 gives us 1 minus 1.5. Again, it's going to be minus 171. So our answer is minus 1.5 amperes for I1. Then of course we do the same thing for I2. Now, of course, here the answer is going to be in the second column. And we repeat the first and second columns. And we do the same thing, find the determinant divided by 114. And when we do that, we're going to get 4 by 24 by 1. And that gives us 96, plus 3 by 6 is 18. And then when we do the bottom side, everything comes to 0. So you can see here, this is 0, this is 0, this is 0. And so that gives us 285. Sorry, it gives us 114. And we divide it by 114, so we get 1 ampere. All right, so this is I2. Next, we have I3. Now we can calculate I3 using this method, or we can also subtract and find I3 according to this equation that we have here. The equation tells us that I3 is going to be what? It's going to be equal to I2 minus I1. So if we do I2 minus I1, let's just try it. So I3 is equal to I2 according to this equation here, minus I1. That tells me that it's going to be equal to minus 1.5 minus 1, which is equal to minus 2.5 amps. So this is what we find using Kirchhoff's current law. Now we can also calculate it using the determinant method and find it as well. So let me calculate it again just so we can see. So again, we need to put the answers, this column in the third column here. So we have 4, 0, 1, 9, 9, minus 1, 3, 24, 0, 4, 9, 0, 9, 1, minus 1 over 114. And that gives us here, we get 216 minus 27. Again, how do we get 216? 9 by 24 by 1 minus what? 1 by 9 by 3, that's minus 27. Then we have minus 1 by 24 by 4. So this is, since we have a minus and a minus, we're going to have a plus 96 over 114. So that comes to 285, and that gives us 2.5 amperes. So again, getting these answers, what do we know? The negative tells us that the current is in the wrong direction. Current direction, wrong. Okay, so what does that tell us? It tells us that our current for I1 is actually not going in this direction, but it's actually going in the opposite direction. So if you were to redraw the circuit, the direction for this current should be in this direction based on how we calculated it using this method. So this is the branch current method. We're going to go next and do the loop. We're going to go and do the mesh current method, right, for the same circuit. Okay, I'll just draw the circuit again briefly. It's doesn't take anything to draw it. All right, the first step we need to do here. First step we need to do is to assign the loop currents. Number 2, we need to then write the KVL equations. Number 3, we need to solve. So write them in standard form or solve simultaneous equations. After we've solved the equations here, then we need to find the branch currents. So how do we do that? Okay, so we need to assume some current directions in the loop. So just to make it easy, I'm going to assume that we have our current IA going this way, and I can assume that IB is going this way. All right, so now I'm going to write the equations in terms of IA and IB. So again, based on the direction of the current, we put the polarity, the positive. Where the current enters the resistor is positive, so current enters here is positive here. Okay, so the next thing we need to do is to write the equation. So let's start right here. So again, same thing, we're going to write the voltage drop here and the voltage drop here should equal to the source, right? So we are saying that 4IA plus 9IA. Now again, if the current direction was opposite here, then the positive would be at the bottom here, and so we would say IA minus IB. But because both of the currents IA and IB are going in the same direction through the resistor is positive here, we can say IA plus IB. And this 2 voltage drops is equal to what? 3 volts. That's all you're saying, right? What about this one here? We can say same thing here. We have 9 IA plus IB plus 6 what? 6 IB is equal to 24. Now we can expand this here. When we expand it, what do we get? We get 4 IA plus 9 IA gives us what? 14 IA plus 9 IB is equal to 3. Expand this one here, what do we get? 9 IA plus 9 plus 6 gives us 15. 15 IB equals 24. All right. So next step now is to solve. So this is the equation that we have. Now we can solve it using substitution. If we try to eliminate one of these, say we try to multiply any of these equations so that if we add the 2 equations, one of the variables goes to 0. That's the easy way to do it. Another easy way is if we just use the matrix method. So we'll do that one quickly. So again, you can see here, we can write the matrix. We have 14 IA here and 9 IB. We have 9 IA here and 15 IB. And we're multiplying, okay, the variables go here, IA, IB. And we get 3 volts here and 24. So 3 and 24. Same thing, we'll do the determinant method. So the primary determinant is going to be equal to, again, this is the primary determinant here. So we multiply these 2, we subtract it from this one. We're going to have 14 by 15 minus 9 times 9, which is 195 here and 81 here. And our answer is 114. All right, so then to find IA, of course, we're going to put the answers in the first column. So we're going to have 3, 24, 9, 15, and we'll divide it over the primary determinant, which is 114. Of course, here we're going to have 3 by 15 minus 24 by 9 over 114. So again, 3 by 15 is 45. 24 by 9 gives us 216. And so when we subtract that, we get minus 171. And we divide that by 114, we get IA is going to be equal to minus 1.5 amperes. Likewise, we can find IB. IB is going to be equal to, again, move the answer column to the second one. So we have 13, 9, 3, 24 over 114 is equal to 15, 24 minus 9, 3, which is 27, 312. And so that gives us 285 over 114, which is 2.5 amperes. So again, now we need to find the branch currents. What's the current here? So IA is equal to I1. So this is the current flowing here, IA. Now keep in mind that it's negative. So it means that the current is actually going in this direction. Then IB is equal to I3. So the current in this direction. And so it's positive. So it means that it's actually in this direction. This is the right one. Now for what about I2? I2, if you look at here, the current going here is actually this one plus this one, all right? So we can say that I2 is equal to IA plus IB, which is equal to 2.5 minus 1.5, and that gives us 1 ampere for 1 ampere for I2, which is for figure 2. We have a different circuit, so I'll go ahead and draw that circuit here. So this is the circuit that we have. Very traditional. Sorry, this is 20 volts and this is 60 volts. And this is 8 ohms, and 6 ohms. So we're told to find this using superposition. All right, find the unknowns using superposition. And so for superposition, we actually you need to solve the circuit using one source at a time. So here you can see we have 2 sources. So we need to solve the circuit using one source at a time. So our steps for this is, number 1, we need to select the source. And then we need to replace all the sources. With a short. If it's this is an ideal source, so replace it with a short. But if it has a resistance, we replace it with the source resistance. Replace all other sources with source resistance. So this is the ideal source. The source resistance is 0, so we're going to replace it for short. Then we say we want to calculate circuit currents. After we calculate the currents, we are then going to repeat that for each source. Then number 5, we are going to add them up algebraically. Add currents. And then important to note, if the direction is different, then of course the currents need to subtract. Add the currents algebraically. Again, if the current directions are different, we need to subtract. So let's go ahead and get started. I'll use this as my source 1. I'll call it S1, and this is S2. So I'm going to redraw the circuit for source 1, all right? So again, I'm going to redraw my source 1. So this is what my circuit looks like. For source 1, which is 60, 8, 8, and 6. So this is my circuit. I've selected source 1 and I've started working with my circuit. The first thing I need to do is to, it says to solve, calculate the circuit currents. To find the total current going here, we need to find the total resistance, right? To find the total currents in this branch, we need the total resistance. And of course to find that, very simple, we can say that RT. If you look at it from this perspective, what is the total resistance? This one is in series and these two are in parallel. If you take this resistor, you just bring it here, you can see that they are clearly in parallel. So the source is equal to 8 in series with what? With these two, right? 6 and 8. So you can say 6 is in parallel with 8, yeah? And so if you expand that, what you get? This is 8 plus, now of course to find the equivalent parallel resistance, we're going to use the product over the sum. So we say 6 times 8 over 6 plus 8, and so we find a solution for that. Don't have my calculator with me, but 6 times 8 will give us, I think, 50, well, is it 48? But our solution is going to be 8 plus this guy here will give us 11.43 ohms, all right? Having this total resistance for this circuit here, we can find the total current, IT. And IT is going to be equal to VS over RS, or RT, which is 60 volts over 11.43 ohms. And that gives us 5.25 amps. Having this total current, so we know that this is the total current going here. We need to find the current going there. And this is where we use the current divider method. So if you want to find I2, we can say that I2 is going to be equal to this resistance, 8 over the total resistance, 6 plus 8, times IT, which is equal to 8 over 14 times 5.25, and that gives us 3 amperes. And of course, we can calculate the other current using the same method, or we can simply subtract it, because we can see here that this current I1 is going to be equal to I2 plus I3. All right, so again, we can see that since we can see that I1 is equal to I2 plus I3, we can say that I3 is equal to IT, which is the same as I1 minus I2, which gives us 5.25 minus 3, which gives us 2.25. So we can see that we have found I1. So we found IT, which is the total current here, and then we found I2, which is the current flowing through here. Then we found I3, which is the current here. Okay. Next step is to repeat it for each source. So now we go to the other source, right? So this is source 1. We can now do source 2. So again, I'll draw the circuit again. So you can see I eliminate the source here, replace it with a short. All right, so our first step here is going to be to find RT, which is going to be 8 plus 6. So again, this is a series with the source, and this one in parallel, 6 in parallel with 8. Now, of course, since we see it's the same as this one, the resistance will be the same. Is equal to 11.43 ohms. Then we can go ahead and calculate IT. IT is Vs over RT, which gives us 20 over 11.43, and that gives us 1.75 amperes for our total current. Now again, what is the direction of the current? We assume our current is coming from the batteries, going this direction. It's going to split up here, right? So this, our main current now is I3. So this IT that we just calculated here is the same as I3. So I'll just put a note here that this is equal to I3, right? So now we want to find, let's find this current here, the same way we did it here. So again, this current here is going to be this resistor over the total resistance. So we can say that I2 is equal to 8 over 6 plus 8. We talked about the current divided before, times IT, which is 8 over 14, times 1.75 amperes, and that gives us 1 ampere. Right, so this is now our I2, and of course we can subtract to find I1. I1 is going to be I3 minus I2. Keep in mind that this is our IT that we found first is the same as our I3, so we're going to say that this is equal to 1.75 minus 1 gives us 0.75 amperes. The last step is to add them algebraically according to the direction. So of course here I have my I1, so sum, we have I1, I2, I3. So what is I1? Okay, I1 is that current here we found here, 2.25. Okay, but I1 is 5.25. I2 we found here was 3 amperes. I3 was 2.25 amperes, right? Now we're gonna write the other current, and if the direction is different, we're gonna change it. So again, if you look at I3 here, the current is different. So for I3, we have minus 1.75 amperes. What about I2? The current is the same, so it's positive, so we're gonna have 1 ampere. What about this one? The current is opposite, so we're gonna have minus 0.75 amperes. And so of course now we add them together. So we get 4 amperes here, we get 0.5 amperes here, and we have 4.5 amperes here. So this is the current that is actually flowing in the circuit with the two sources. Now this is the current you use to calculate the voltage drop here. Okay, so we are done with this circuit using the superposition theorem. Now we will do the same circuit using the nodal analysis method. again. So as you can see, this exercise is not about memorizing, but it's about using the different techniques to get the answer. So I'm going to draw my circuit up here, maybe just draw it a little smaller. So first step in nodal analysis, the steps, we need to establish a node. Then we also need to establish or assume current direction, branch currents. And then we write the branch currents with reference to that point here. So I'm going to call this point A. So I'm saying that the voltage at this point is A. That's the same voltage across the 6 ohm resistor is the voltage if you minus the voltage drop here or the voltage drop there. So this is the branch, assume branch currents. Then we're going to write the branch currents with reference to A. Write the KCL with reference to A. And of course, then we will solve for A, and then we can solve for currents. All right, so let's try to do this. So again, here, let's just assume that the current is coming from here, and then the current is going down here. So these two currents are adding up together. Of course, we'll call this one I1. This one is going to be I2. This one's going to be I3. So if you write the KCL is going to be, for this equation, I2 plus I3 is going to be equal to I1, or we can say that I1 minus I2 plus I3 is equal to 0. Now we're going to rewrite that with reference to A. Now again, so we can say what is I2? The voltage across here is going to be the voltage over the resistance, so it's going to be A or VA over 6 ohms. So this is going to be minus VA over 6. What about the voltage drop here? So again, the current here is the voltage drop divided by the resistance. The voltage drop is actually the source minus A, right? So it's going to be here 60 minus VA over 8. This one likewise is going to be 20 minus VA over 8. Again, if you start with 20, you drop some, you end up with A. So what was that you dropped? You actually dropped 20 minus VA. The next thing we need to do is we need to go ahead and get the common denominator for these guys here. So let's say the common denominator is going to be 24. So I'll write it on this side. So let's say we have let's do the common denominator of 24. 24 into 8 is going to be 3. So it's going to be 3 times 60 minus VA. Then we have minus 4 VA plus 3 VA. Sorry, 3 times 20 minus VA. All right, so again, 24 into 8, 3, and the 3 goes at the top here. So this is equal to 0. So then we need to move the VA out. So when we move VA out, then since we have 24 on both sides, it will cancel out. So we're going to have here, so if we move the VA out, we're going to have 3. Now we can begin to expand them. So 3 times 8 is going to be 180. 180 minus 3 VA plus 60 minus 3 VA is equal to 4 VA. Now again, the 4 goes on this side, it becomes 4 over 24, and all of this will still be over 24. And of course, this is going to cancel out each other. If we multiply both sides by 24, then the 24 at the bottom will cancel out. Okay, so here we have this here. Our next step is to solve for VA. So what is VA? All right. So of course, we can continue the algebra right here, and we can see that if we take this 3 VA minus 3 VA, we put it on this side, it's going to be 4 plus 3 VA plus 3 VA, which will give us 10 VA. So it tells us that 180 plus 60 will be equal to 10 VA. Of course, we can calculate that VA is going to be equal to 240 over 10, which gives us 2.24. So VA is 24 volts. All right. Now we can solve for the different currents based on this equation right here. So I1, I2 is going to be equal to minus VA over 6, which is minus 24 over 6, which gives us minus 4 amps. What about I1 is 60 minus VA. So 60 minus VA, 60 minus 24 over 8, which is 4.5 amps. What about I3? I3 is equal to 20 minus VA, 24 over 8, which gives us minus 0.5 amps. So this is the same answers that we got using the superposition theorem, and we get the same answers if we use the nodal analysis method. So after what you're supposed to do afterwards, you're supposed to just put your answers in this table here, so that the simulation result you can see in the simulation, and the other answers you can put here, and pretty much they're the same. So for nodal analysis, for I1 we have 4.5. For I2 we have minus 4. Amps. Of course, for I3 we have 0.5 amps. Again, the negative tells us that we had a wrong direction. So the current is actually going this direction and also this direction. So since I have also the superposition, I'll put the answers as well. Okay, hold on. Where's the superposition? Okay. I think this should be superposition here. Superposition. We have 4.5 amperes, we have 4 amperes, and 0.5 amperes. So how do you find the voltages of this resistance? You just simply multiply the current, so I, the current in this resistance, by the current. So 8 by 4.5 gives us 46 volts, and 6 by 4 gives us 24 volts, and for this one we have 8 by 0.5 gives us 4 volts. So this is how you find and of course it's the same here. And of course you will look at the simulation, and when you calculate the branch current method, you can put your results in here. We did calculate the branch and loop for and I wrote my answers the wrong place, so this should be, so I'm gonna just change this. This is for figure 2 and this is for figure 1. So for figure 1 we have the branch and loop, and they are going to be the same. For I1 we had 1.5, I2 1.0, I3 2.5. This is for the branch. For the loop, same thing. 1.5, 2.5, 1.0. Of course, how do we find the voltage across the resistors? For the first one is we have a 4 ohm resistor, so 1.5 times 4, that gives us 6, I believe. So this is 6 volts. For I2 we have a 9 ohm resistor, so I times R, so 1 ohm times 9, this is 9 volts. And for V3 we have a 6 ohm resistor, and the current is 2.5, so 2.5 times 6 gives us 15 volts. And it's going to be the same here. All right, so for your assignment, you need to calculate those, sure you're working, and you will fill in the table here. For figure 1, for figure 2, same thing. You're going to do the nodal analysis and superposition for this. Of course, you will get the simulation results and you can write it in there as included in the lab.